Suppose the car moves along a straight line from start to finish. So the displacement the car makes is the r vector. The magnitude and direction of the r vector give the distance and the direction traveled along the straight line. So the direction would be this angle that the r vector is making with the x-axis. However, the car could also arrive at the finish point by first moving due east and then turning through 90 degrees and then moving due north, like this. So goes due east, turns 90 degrees, and goes due north. This alternative path is shown in this drawing and is associated with the two displacement vectors, x and the y vectors. The vectors x and y are called the x vector component and the y vector component of r. So vector components are very important in physics and have two basic features that are apparent in this picture. The first one is the components add together to equal the original vector. So I can write r vector equals vector x plus vector y. The other feature of vector components that is apparent in this picture is that x and y are not just any two vectors that add together to give the original vector r. They are perpendicular vectors. The perpendicularity is a valuable characteristic as we will see soon. So any type of vector may be expressed in terms of its components in a way similar to this one. So if you take an arbitrary vector b, for example, or vector a, doesn't matter. Let's call it vector a, an arbitrary vector. So this will have its x component and a y component. So the x component would be the vector that is going to the east, and then perpendicular vector that is going to north, and that would be the ay component of vector a. As you already noticed, vector a equals vector x component of vector a plus y component of vector a. There are times when a drawing such as in this figure is not most convenient way to represent vector components. There is an alternative method that we can present them, where you can just simply start from the head of the vector a and then projection of the vector a on the x-axis will give you the ax vector, and the projection of vector a on the y-axis is y component of vector a, which are still perpendicular to each other. Now, as for definition, in 2 dimensions, the vector components of vector A are two perpendicular vectors, ax and ay, that are parallel to the x and y axis, respectively, and add together vertically according to A equals ax plus ay. It is often easier to work with the scalar components of ax and ay instead of vector components of ax and ay. Usually scalar components are positive or negative numbers with units that are defined as follows. like the scalar component ax has a magnitude equal to that of a vector ax and is given a positive sign if ax points along the x-axis, a negative if the vector ax points along the negative x-axis. Let me just write a kind of a chart so it would be easier to understand. Okay, let's take this vector component. Ax vector is a 8 meter directed along the positive x-axis. Ay is a 10 meters directed along negative y-axis. So the scalar component for ax vector would be ax, because its positive x-axis will be equal positive 8 meters. For the ay, it is along the negative y-axis, so ay equals negative 10 meters. So that would be scalar components. So we want to draw these vectors that would be, let's say, x and y axis first. Choose your axis to be positive y, positive x going to the right, the conventional one. Now I'm going to draw my ax component, which is positive 8. Let's say here's a 8 meters. Okay, so this would be my ax, and then ay is negative 10, and I would draw this directed downwards. So, and suppose that here we have a negative 10 position, so this would be my ay. Now you might ask, where is the actual vector a here? Because, well, you are supposed to add ax and ay together as vectors and add them up and get the vector, but these are not in a head-to-tail, they're not put at head-to-tail. So what you do, the best thing to do is make a parallelogram. Sometimes it's known as a parallelogram method, and the diagonal of this parallelogram would be your vector a right here. Well, usually in our lectures or in the book, when we use a term component, we will be referring to a scalar component unless otherwise it's indicated. Another method of expressing vector components is to use a unit vector. So let's add this as a unit vector. So unit itself already tells you the word unit. It means a vector that has a magnitude of 1, uno, unit. Okay, so but it has no dimensions. It's just a number. Okay, so for example, if you draw an x and y axis, okay, so the unit vector would be just the vector that is directed to the positive x-axis and has a length of 1, and then there is this other vector that is pointing towards the positive y-axis, has a length of 1. So this is known as a unit vector. So a notation for a unit vector would be x and a hat on the top. On the left, for the y would be y and a hat on the top. So x and y hats are dimensionless unit vectors of length 1 that point in the position x direction and y direction for the y hat. So now these unit vectors, for example, you can make any vector represented in terms of unit vector. For example, let's say we want to draw our ax vector component, right? AX component. So here's our AX component. And a AX vector component is the length of the vector multiplied by the unit vector. So you could write AX vector. If you want to drop the arrow, you need to do AX equals the magnitude of the AX times X hat. Okay. Similarly, we can write a Y vector equals a Y hat. So if we go back to our example as a unit vector for our vector component AX, we would write AX equals positive 8 meters X hat, and AY equals negative 10 meters Y hat. Then I can write vector A equals AX X hat plus AY Y hat. For our example, right here, I could write vector A equals 8 meters X hat minus 10 meters Y hat. That would be the vector representation in a unit vector form. If the magnitude and direction of a vector are known, it is possible to find the components of the vector. The process of finding the components is called resolving the vector into its components. Let's take a look at an example. Suppose the displacement vector r has a magnitude r equals 175 meters and points at an angle 50 degrees relative to the x-axis to positive x. So we want to find out the x component of the vector and the y component of the vector. So for better understanding, let's picture the situation. So we have two x and y vectors, component vectors. So this is my y component, and then here's my x component of the vector r. And we will base our solution on the fact that this triangle that is formed by the vector r and its components x and y is a right triangle, meaning I have a 90 degrees in here. And then we know this angle right here is a 50 degrees. So if we use the definitions of trigonometric functions where the sine theta was equal to opposite side over hypotenuse and cosine theta equals adjacent over hypotenuse, and tangent theta equals opposite over hypotenuse. In this case, we have sine theta that involves the y over r, and then cosine theta involves x over r, and tangent theta involves y over x. Please note that when I'm talking about this theta, this is the theta that equals 50 degrees. Well, sine, if you take this other angle, let's call it alpha. For alpha, sine theta will not be y over r. Sine alpha will not be y over r. So we can write sine alpha equals, opposite would be the x over r. Cosine alpha would be, adjacent side would be the y over r. And for tangent alpha, that would be opposite over adjacent, which is x over y. As you can see, depending at what angle are you looking at, so your sines and cosines will have different expressions. So in our case, we're interested in an angle 50, which corresponds to our theta. So therefore, to find the, for example, y component, I will use the sine function, and for finding the x, I will use the cosine function. So let me rewrite that in here. So I will have sine theta equals y over r, and then I can find the y from here, that equals r sine theta. Similarly, I can write cosine theta equals x over r, and then x equals r times cosine theta. All I need to do, plug in the numbers. So let's start. Y equals 175 meters times sine 50 degrees. And when we plug this into calculator, we will get 134 meters. We can do the same thing for the x component. That is 175 meters times cosine 50 degrees. And when we put that into calculator, we'll get 112 meters. I'd like also to show that the values of x and y's found through the angle alpha will give you the same result anyway. So let's check that. Okay, so we have if we have in this triangle 50 degrees, 90 degrees, then alpha should be 90 minus 50 degrees, which is 40 degrees. That is because all three angles add up to 180 degrees in a triangle. So if I use this expression to find the x, that would be x equals r sine alpha, which is 175 meters times sine 40 degrees. If you punch this into calculator, you will get 134 meters. The same as we got, oops, it's not the same. Actually, I miscalculated. This is 112. Same as x. Now, same thing we can do for the y, that equals r cosine alpha, which is 175 meters cosine 40 degrees, and that will give us 134 meters, which is the same as we found for theta. Well, since the vector components add the original vector from the right triangle, the Pythagorean theorem can be applied to check the validity of calculations. For example, I could say r equals square root of x squared plus y squared, and then plug in the numbers and see if that will work. So for the x, we found 112 meters squared. plus for the y we found 134 meters squared. So if you punch this into your calculator, you will get this equals 175 meters. That's exactly what we had originally, which means our solution is correct. So one more thing about the vector components, and then we will be done. It is possible for one of the components of vector to be 0. This does not mean that the vector itself is a 0. However, for a vector to be 0, every vector component must individually be 0. So in 2 dimensions, saying that vector A equals 0 is equivalent to say, is the same to say that AX, the X component, is 0 and the Y component is also 0. Or stated in terms of a scalar components, if vector A equals 0, then AX equals 0 and AY equals 0. 2 vectors are equal if and only if they have the same magnitude and direction. So vector A equals vector B if vector A equals vector B, then vector X component of vector A should equal X component of vector B, and Y component of vector A should equal to Y component of vector B. So these conditions should apply if 2 vectors are equal to each other.